projects. In this video, we are going to explain about the project title, an attention-based convolutional neural network for intrusion detection model. Introduction. Network technology is widely used but susceptible to cyber attacks. Intrusion detection systems, IDS, are crucial for detecting and responding to these attacks. Machine learning and deep learning models are now being employed for more effective IDS. While machine learning-based IDS perform reasonably well, they struggle when faced with complex attack patterns. To effectively detect these patterns, superior feature extraction methods are required. Deep learning models like convolutional neural networks (CNN) have shown promise in handling intricate patterns due to their ability to create robust feature representations from data. CNN, convolutional neural network, excel in handling complex tasks by converting data into image-like representations, enabling them to analyze and learn from these features effectively. Attention mechanisms, a part of deep learning, are employed to assess the significance of various features. These mechanisms have proven effective in enhancing the performance of IDS intrusion detection system by focusing on important features. The project aims to combine the strengths of CNN and attention mechanisms specifically tailored for intrusion detection. This model intends to optimize the extraction of essential information from features while also maintaining computational efficiency, resulting in a more effective and efficient IDS, intrusion detection system. Objective. The primary aim of this project is to create an intrusion detection model by leveraging convolutional neural network CNN enhanced with attention mechanism. This integration is geared towards not only enhancing computational efficiency but also effectively evaluating the importance of extracted features from network data, thereby improving the overall performance of the intrusion detection system. The project intends to establish a robust mechanism capable of actively monitoring network traffic within systems. By analyzing this traffic in real time or near real time, the goal is to swiftly identify and prevent potential security threats, ensuring timely action to mitigate risk and protect the network infrastructure from malicious activities. Emphasis is placed on integrating attention mechanism directly into the architecture of the convolutional neural network. This integration is specifically designed to evaluate the relevance and significance of various features extracted from network data. By assigning appropriate weight values to these features, the model aims to effectively discern between normal and malicious network behaviors, enhancing the accuracy of threat detection. The proposed model strives to strike a balance between shift threat detection and high accuracy. Through comparative experiments conducted on a subset of the CIC IDS 2018 dataset, the project seeks to demonstrate the model's ability to swiftly and efficiently identify security threats while maintaining a high level of precision in its detections. This validation process aims to showcase the effectiveness of the model in real-world scenarios. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing the packages. This initial step involves importing essential libraries and packages required for various tasks in the project. For instance, pandas used for data manipulation and analysis with its data frame structure. NumPy essential for numerical operations and handling arrays. Matplotlib and Seaborn visualization libraries used to create plots and graph for data exploration. Keras and TensorFlow frameworks used for building neural network models. Exploring the dataset. CIC IDS 2018. This phase involves loading and examining the CIC IDS 2018 dataset to understand its structure, columns, data types, missing values, and statistical summaries. It's crucial to gain insights into the data before processing. Data processing, Pandas data frame, and Keras data frame. The dataset is converted into Pandas data frame format for ease of handling and manipulation. Additionally, a Keras compatible format is prepared for modeling purposes. Dropping unwanted column. Irrelevant or redundant columns, if present, are removed from the dataset to streamline further analysis and model development. Visualization using Seaborn and Matplotlib. This stage involves creating visual representations of the dataset. It includes histograms, scatter plots, heat maps, or other visualization to explore relationships, distributions, or patterns within the data. Label encoding using label encoder. Categorical data is often converted into numerical format for machine learning models. Label encoding, utilizing tools like the label encoder from scikit-learn, transforms categorical labels into numerical representations. Feature selection. Select percentile using mutual info classify. Feature selection is crucial for model efficiency. Select percentile coupled with mutual information has a metric is employed to choose the most informative features for the model while discarding less relevant ones. Splitting the data to train and test for deep learning. The dataset is divided into two subsets, a training set and a testing set. The training set is used to train the neural network model while the test set evaluates its performance. Building the model. This crucial step involves defining the architecture of the attention-based convolutional neural network CNN, specifically designed for intrusion detection. Here, layers are configured, activation functions are chosen, and the model is compiled for training using appropriate optimizers and loss functions. Training the model. This phase involves feeding the prepared training data into the neural network model that was defined earlier. The model undergoes a training process where it learns to recognize patterns and features from the input data. The model's parameters are adjusted iteratively to minimize the prediction error. Flask framework with SQLite for sign-up and sign-in. Flask, a Python web framework, is utilized to create a web application for user authentication, sign-up and sign-in functionalities. SQLite, a lightweight database, is employed to store user information securely. User gives input has feature values. Users interact with the web application by providing input in the form of feature values related to network traffic or system data. These inputs serve as the basis for the intrusion detection prediction. The given input is pre-processed for prediction. The feature values entered by the user need to undergo pre-processing to match the format expected by the trained model. This pre-processing ensures that the input data aligns with the structure and requirements of the model for making predictions. Trained model is used for prediction. The pre-processed input data is fed into the trained neural network model. The model utilizes its learned parameters and architecture to make predictions or classify the input data as normal or indicative of an intrusion. Final outcome is displayed through front end. The final outcome of the prediction, whether it indicates a normal network behavior or identifies potential intrusions, is displayed to the user via the web application's front end. This outcome provides insights into the security status of the network based on the input data provided by the user. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm used in the project is CNN, Convolutional Neural Network. CNN are widely used in computer vision tasks due to their ability to effectively capture spatial patterns within data. In intrusion detection, CNN, Convolutional Neural Network, can be adapted to process network traffic data as image-like representations, identifying spatial patterns that signify different types of intrusions or anomalies. In this project, the CNN is the core architecture for feature extraction from network data. Its layers perform convolutions and pooling operations to detect meaningful patterns that can help identify potential intrusions. DNN, Deep Neural Network. DNN, or fully connected neural networks, are adept at learning complex relationships within data. In intrusion detection, DNN are employed in conjunction with or subsequent to CNN layers to further process extracted features and make complex decisions based on hierarchical representations. After feature extraction by the CNN, a DNN is utilized to learn and classify these features into different intrusions or normal behavior categories, enhancing the model's ability to accurately detect network intrusions. BiLSTM, bidirectional long short term memory, or bidirectional encoder representations from transformers. These models, especially BiLSTMs and transformer based architectures like BEIT, excel in capturing sequential and contextual information within data. In intrusion detection, they are utilized to understand temporal dependencies and long range dependencies between network traffic sequences. BiLSTMs or transformer based models are employed to analyze the temporal sequence of network traffic data, capturing nuanced patterns and dependencies that signify anomalous behavior or potential intrusions. In the context of intrusion detection, these algorithms are leveraged for their abilities to process and understand complex patterns within network data. CNN focus on spatial patterns, DNN handle learned hierarchical representations, while BiLSTMs or transformer based models excel in capturing sequential and long range dependencies, collectively contributing to the detection of potential network intrusions. As an extension, we applied an ensemble method combining the predictions of multiple individual models to produce a more robust and accurate final prediction. Comparison graphs. Comparison graphs offer a visual breakdown of how a model performs across essential evaluation metrics. Models are compared with the parameters accuracy, precision, recall, and FN score. This is the accuracy comparison graph. On the x-axis, we have accuracy score, and on the y-axis, we have algorithm name. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have precision score, and on the y-axis, we have algorithm name. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is the recall comparison graph. On the x-axis, we have recall score, and on the y-axis, we have algorithm name. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the F1 comparison graph. On the x-axis, we have F1 score, and on the y-axis, we have algorithm name. F1 score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. I'm copying the path and then open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. So here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are a new user, we need to register first. So click on sign up button here. So here we need to enter all these details to register. But I have already registered, so click on sign in. Here we need to enter the username and the password which we have created and then click on login. We have logged in successfully. So here we need to enter these parameters to predict whether attack is detected or not. Before entering the parameters, let us understand the parameters. So here the first one is forward packet length standard deviation. It measures the variability or dispersion of the lengths of packets sent in the forward direction in a flow. Forward packet length mean represents the average length of packets sent in the forward direction in a flow. Forward packet length maximum denotes the maximum size of packets sent in the forward direction in a flow. Forward segment size average indicates the average size of TCP segments transmitted in the forward direction in a flow. Packet length standard deviation measures the variability or dispersion of the lengths of all packets in a flow regardless of direction. Flow interarrival time standard deviation represents the standard deviation of interarrival times between consecutive packets in a flow. Backward packet length standard deviation measures the variability or dispersion of the lengths of packets sent in the backward direction in a flow. Backward segment size average denotes the average size of TCP segments transmitted in the backward direction in a flow. Packet size average represents the average size of all packets in a flow irrespective of the direction. Subflow forward bytes indicates the number of bytes sent in the forward direction within a subflow. These parameters signify various characteristics and statistical measures of network traffic data, providing insights into packet lengths, size, interarrival times, and directionality within flows, which can be crucial for feature analysis and modeling in intrusion detection systems. Now, we will enter the parameters value. So I'm entering the parameters value. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is an attack detected. Attack type is DOS. Now we will enter another set of parameters and check whether attack is detected or not. So here I'm entering another set of parameters now. So here I have entered all the parameters. Now click on predict button. So here we can see we got the result. There is no attack detected. It is normal or benign. In this way, by entering the parameters, we can predict whether attack is detected or not. Now click on sign out button. The conclusion of the project is the proposed model aims to enhance computational efficiency while integrating attention mechanism into the CNN architecture for better intrusion detection. By optimizing computational processes and leveraging attention mechanism, the model intends to efficiently analyze and prioritize features in network data, thereby enhancing its ability to detect intrusions. The model focuses on utilizing feature information efficiently, organizing it in a structured format resembling images for enhanced processing. By organizing features into an image-like structure, the model streamlines the processing flow, enabling more effective utilization of feature information to detect intrusions accurately and swiftly. The model aims for a balance between speed and accuracy in intrusion detection. Comparative experiments conducted on a subset of the CSC CIC IDS 2018 dataset aim to showcase the model's ability to swiftly and accurately identify potential intrusions, providing empirical evidence of its effectiveness. The project emphasizes the robustness of deep learning models, particularly CNN, in handling complex attack patterns prevalent in network data. CNN, known for their ability to capture intricate patterns, are highlighted for their potential in effectively detecting and mitigating network intrusions. Integrating attention mechanism within the CNN model enables the assessment of feature importance. By assessing feature importance, the model enhances its overall performance in intrusion detection by focusing on critical features, thereby improving accuracy and effectiveness.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.